SwayamPrabha. Digital India. Educated India.
Good afternoon, everybody. Today we will do something little different. We'll work on application of our knowledge to a problem of practical interest and setting up an algorithm for computer solution. How to set up the algorithm, we will experience that through today's lecture, and we'll take up a problem which often occurs in metallurgical industry. So problem statement is the following: consider a metallic square block shown in the figure, and this square block is initially heated at a temperature T0, which is much higher than the ambient local ambience or ambient temperature. The dimension of one side, any side of this block, is L. The block is infinitely long, very long block in Z direction. So we are looking at X and Y direction. Z direction infinitely long means Z direction dimension is much higher than X and Y direction dimensions. The thermal diffusivity of the metal is alpha. The physical boundary conditions have been explained. See, all around it is being cooled by the local fluid, and obviously this is minus K del T del X on this surface equal to H T minus T infinity, convective boundary condition, which is basically Neumann condition, you can also say, or mixed condition, you can say rather. We have two tasks. One is identify the solution domain and specify the problem, and second is write a detailed algorithm to find out temperature distribution on the surface of interest. We can see the surface using ADI method. So first is setting up a problem. That is quite simple. Considering so we can see that here we can draw, since all around the confining surfaces same boundary condition, so there is a vertical symmetry and there is horizontal symmetry also. So if we use these two symmetries, vertical symmetry and horizontal symmetry, then we can make use of del T del X equal to 0 on this surface and del T del Y equal to 0 on this surface, which in our computing language we can call symmetric boundary conditions. So considering the vertical symmetry and horizontal symmetry, the top right hand side quadrant can be considered as a solution domain. As such, any quadrant can be taken as a solution domain. We are taking top right hand quadrant as a solution domain. And the governing equation is del T del temperature del time del T del time equal to alpha del 2T del x2 plus del 2T del y2. Alpha is the thermal diffusivity, K is the thermal conductivity, H is the convective heat transfer coefficient. We have already this geometry we have seen, and the initial temperature of the block is T naught, which is we have said higher than ambient temperature, so it is a cooling problem, and T infinity is the ambient temperature, T naught is greater than T infinity. That is the physical interpretation of the problem. Now we can see that character wise this is basically 2D unsteady heat conduction problem. So we have already experienced that in our course. We have done some exercise how to solve this problem. We will apply ADI method, that means alternate direction implicit. So, and instead of going from one level, say nth level to n plus 1th level through one time step delta t, we will divide the time step delta t by 2, and through delta t by 2 first we will progress n plus half level from nth level, and then from n plus half level again we will go to n plus 1 level. So when we go from n to n plus half level, we right hand side the x direction derivatives we express in terms of finite difference quotient, and this is simple central difference, but at the time level we are writing n plus half. And in y direction also we are applying simple central difference, but we are retaining the temperatures at nth level. So from here it is possible to calculate the temperatures at n plus half level through implicit formulation. Having known n plus half level temperature, we come to steps 2. Then x direction we retain again terms corresponding to n plus half level, and here the temperature is discretized del 2t del x2 using central difference. But in y direction we write the variables at n plus 1th level, and obviously the temporal derivative is at ij point t n plus 1 minus tij n plus half. So, and this through this step we are going from tij n plus half to tij n plus 1 level, and time step is delta t by 2. This is a usual thing we have learned. So in 2 steps we proceed, first from n to n plus half, then n plus half to n plus 1. Arranging both the equations in the form where unknowns are on the left hand side and knowns are on the right hand side. So for step 1, all the equations, all the terms that are expressed at n plus half level will be taken on the left hand side. These are not known, and terms which are at nth level will be kept at right hand side. These are known. Having done that, when you will go for step 2, all the terms that are written at n plus 1th level will come to left hand side, and terms at n plus half level will be retained on the right hand side. Exactly we do that, and here while doing so, this alpha delta t by delta x square we call it Rx, and alpha delta t by delta y square we call it Ry. So we are writing Rx by 2 Ti minus 1j, 1 plus Rx Tij, Rx by minus Rx by 2 Ti plus 1j. So Tij is expressed in terms of Ti minus 1j and Ti plus 1j, all are at n plus half level, and right hand side all the terms are retained at nth level and all the terms are known. Similarly, from equation 2, again we write Ry by 2 Ti j minus 1, Tij multiplier is 1 plus Ry, and Tij plus 1 multiplier is Ry by 2. These are all n plus 1th level. Right hand side all the values are n plus half level, and now all the n plus half level values are known to us. And let me again say that Rx is alpha delta t by x square and Ry is alpha delta t divided by delta y square. Let me repeat again. Rx is alpha delta t divided by delta x square and Ry is alpha delta t divided by delta y square. So these are the equations, equation 1 and equation 2, and we can see that this is implicit formulation. Here if we can if we can vary I from the first point to last point and y from first point to last point, we will get some matrix and we'll be able to solve that, and hopefully formulation should be such we will get tridiagonal matrix for step 1, and also we will get tridiagonal matrix from step 2. That is the whole purpose of doing ADI, because inverting tridiagonal matrix is simple and solution can be obtained very easily. We have already seen how it functions, and very simple algorithm, only the diagonal elements are to be changed and right hand side vector, resultant vector has to be changed, and then we will get the solution very easily through back substitution. So now the physical domain, that means the metallic block, we are taking the top right hand side top coordinate, top section, top quadrant, where we can lay the grids, and the boundary conditions are, we have already said on this. Let us start from A. So bottom surface, if this direction, x direction counts are I, so I equal to 1 to I max, all the points, these are del t del y equal to 0. Symmetric condition, del t del y equal to 0. Then we'll go to B. B is again the left extreme, which is also symmetric condition. So j equal to 1 to j max, all the points, del t del x is 0. So symmetric condition from the geometry. And then C is convective condition. So since this point has been covered by this boundary condition, and this is likely to maintain the symmetry on this direction, so we are here applying this from 2 to I max minus 1. We are leaving the last cell, because last cell again boundary condition from this side will be defined. So 2 to I max minus 1, the boundary condition is k del t del y plus t ht equal to h into t infinity. So basically k del t del y plus h into t minus t infinity equal to 0. That we are translating in this way. And the right hand boundary, again convective condition, basically whatever is the temperature, there is a heat flux based on the temperature at the end surface to the local ambient fluid, and it will depend on the convective heat transfer coefficient H. So heat flux is K del T del X, and the thermal energy which is taken away by the fluid is H T minus T infinity. So basically we can write this equation. Actual condition is minus K delta del T del X is H into T minus T infinity. Here also minus K del T del Y into del T minus K del T del Y is equal to H into T minus T infinity. So these are the physical explanation of the boundary condition, and this we have to, and this again here 2 to J max we apply this condition. T is the temperature of the end node everywhere, all these end nodes, this T corresponds to that. And the total domain, this is 1 to I max. I max may be 10, maybe 20, maybe 30, maybe 40, and this direction J equal to 1 to J max. Same, J max can be 10, 20, 30, 40, whatever is the grid size we want to deploy. Now we have to, this we have not done earlier. All the boundary conditions are to be converted into equations. How? A, for example, and these are applicable to the equations 1 and 2. So when this will be applicable to equation 1, all the temperature boundary conditions will be found out from here, but temperatures are at n plus half level. So here basically del T del Y is 0. That means temperature at this cell, at this point, temperature at this point, if we subtract this minus this and divide by delta Y, that means we are setting up del T del Y is 0. So we have exactly done del I2 n plus half minus del I1 n plus half by delta Y equal to 0. I we are keeping as dummy variable here. I can run from 1 to I max or 2 to I max minus 1. That means for all these cells we can, here 1 to I max we can run. So we are setting up basically symmetric boundary condition. Then from B means this one. This is del T del X 0. In X direction it is symmetry at this line. So T2j minus T1j by delta X del T del X. This is at n plus half, this is at n plus half equal to 0. This is equation 4. Then from C we will write basically K Tj max minus Tij max minus Tij max minus 1. That means Tj max minus Tij max for all i's and Ij max minus 1 for all these points. We are writing difference by delta Y, that means K del T del Y plus H into Tij max, the endpoints. This T corresponds to, I told, at J max points equal to H into T infinity. So from C we have been able to write that. Then from D again same thing, k del t del x. That means if this is Imax, all Imax points, j is this is at j equal to j max, all Imax points are I equal to, this is 2, this is equal to 3, I equal to 4. So basically again little mistake, this is j equal to 1, j equal to 2, j equal to 2, j equal to 3, j equal to 4, and so forth. But every point I coordinate is I max. So we can write I max j minus I max minus 1j. So these are all Imax points at different j's, and Imax minus 1 means this, all these points, difference between them by delta x, that means del t del x. So k del t del x plus h into again t Imax j1, t Imax j2, t Imax j2, t Imax j3, t Imax j4, like that. So Imax j equal to h t infinity, and these are all temperatures at n plus half level. So these are boundary condition for step 1. Step 2 also we will apply, same is the boundary condition, but here we will apply, same are the boundary conditions, but here we have to apply them at n plus 1th level, and we have done that. So again the same, we can see that del t del y equal to 0. That means here t I equal to 1, and here this is I equal to 1, j equal to 1, I equal to 2, I equal to 3, I equal to 4. So I will be varying, and here again I equal to 2, I equal to 3, but j is all 2, all j's are 2. So all these all these temperatures and these nodal temperature are subtracted from the corresponding nodal temperature delta y below divided by delta x. That means ti2 I is varying from 1 to I max, ti1 again I is varying. That's what we are saying. We are basically fixing j coordinate to 2 and 1 divided by delta y. That means setting up del t del y here, and that is equal to 0. Similarly, we are setting up here, we are fixing I coordinates, and that means all I2 to I1, I2j to I1j. J is varying from 1 to j max. So basically through this we are setting up del t del x on this surface, and that is del t del x equal to 0. So basically we are not really changing anything, only we are changing all the temperatures we are writing at n plus 1th level. For step 2, we wrote the boundary conditions 3, 4, 5, 6, all the temperatures at n plus half level. Similarly, on the same boundary, we are writing boundary conditions at n plus 1th level. We are just giving the equation number 7, 8, 9, 10. Now we will see how we run the sweeps. So solve equation 2, 1 and 2 together with the boundary condition using tridiagonal matrix formulation. Step 1 is now for each j. So if we are located at this j, this j, this j, each j, we can have tridiagonal matrix by varying I equal to 2 to I max minus 1. So 2 to I max minus 1. Why we are varying from 2 to I max minus 1? Because when we are at, for example here, this is T 2, 2, but T I equal to 2, j equal to 2, but this is, if this is Tij, when we are writing equation here, this will involve Ti minus 1j, and I minus 1j means this point. Similarly, when we will come here, this coordinate of this point is basically I max minus 1 j, I max minus 1, here j equal to 1, but I max minus 1 is the I location. So if this is ij, this will involve I plus 1j. That means I max minus 1 will involve I max at j equal to 1. So basically we are j equal to 2, sorry. So at j equal to 2, we will vary I from 2 to I max minus 1, and when we are at 2, I equal to 2, eventually it will involve in the finite difference equations I minus 1, which will be the boundary condition. When we are at I equal to I max minus 1, then it will involve Ti plus 1, which is the boundary condition. So all i's are varied from 2 to I max minus 1. Boundary conditions will be taking care of I minus 1 and I plus 1 extremes, and we will be able to form a tridiagonal matrix at j equal to 2. Similarly, j equal to 3. Similarly, j equal to 4. So at each j, we will form a tridiagonal matrix system. After solving at each j, we will get the entire row. So we were going from one j to another j and completing the entire row. And since we are progressing in j direction, we will call it j sweep. But while doing the j sweep, observe two things. One is, at any j, I is varying from 2 to I max minus 1. I have explained why. Because this will take care of the boundary conditions at the left extreme and right extreme if we vary it from 2 to I max minus 1 and form the tridiagonal matrix. Now, also when we are doing j sweep, we'll do it from j equal to 2 to j equal to j max minus 1. We will leave these endpoints because these endpoints will come from boundary condition. We are not now getting involved in it. We are j equal to 2 will, because if we then work on this tridiagonal matrix, we will see everything is known and we'll be able to find out values at all points at this row. Similarly, j equal to 3 will be able to find out all values, all temperature values at the next row. So for each row, we need a tridiagonal matrix, and j will take care of the variation of row. J will run from 2 to j max minus 1, and I also for each tridiagonal matrix, we will run it from 2 to I max minus 1. Now, while forming the matrix, we can the boundary conditions, we can, as I said, that the left boundary, it is taken care of 2ij minus t2ij minus tij by delta x, that means del t del x at any j, del t del x at n plus half level. So the left hand side boundary will be handled by this equation, which was equation 3 actually. Let me check it again, which was which was equation 4. So this is equation 4 and this is equation 6. If you look at it, and this is equation 6 will be basically the extreme right boundary, again k del t del x plus h into t at the point of interest into h into t infinity, equal to h into t infinity, minus k del t del x equal to h into t minus t infinity, that boundary condition for the extreme right. And then we can write down the entire matrix this way. Now we'll explain it again. You can see this boundary condition has been the first row. You can see, this is t1ij, next term in this column is t2ij, and this is minus 1 t1ij minus 1 t1ij. This is plus t2ij. This is t2ij. So this matrix has been formed. The first line of the matrix I am reading, equal to 0, equal to 0. Intermediate all points 2 to I max minus 1 will be guided by equation 1, right? This is will again, if you recall, will be through equation 1. So all intermediate points 2 to I max minus 1 is handled by this elements of this matrix, and each for basically we will get a tridiagonal matrix. That means each equation will have 3 terms, ij, I minus 1j, I plus 1j at n plus half level unknown. So this will create 3 diagonals. It will run, and right hand side all the terms unknown will be this term, depending on, again, I equal to 2, 3, 4, this I will keep on varying in this, j has been kept fixed. So these are all known terms, and finally this n boundary condition, extreme right boundary condition, if you look into this equation, you can get even term by term here, like you can get minus k delta x into t I max n plus half. So t I max j n plus half k by delta t, this term you will see will be associated with this, and since this is I max j, this is also I max j. So here you can see t I max j, this term here it has a coefficient k by delta x, here it has a coefficient h. So k by delta x plus h, this will be the last element, multiplied by t I max j n plus half. and its just previous element is minus k by delta x. You can see minus k by delta x, t I max minus. So when we multiply by this column, so this its multiplier is basically t I max minus 1j, basically this element, right? So that will be the last equation. So this term is here arising out of this del t del x term, and right hand side is h t infinity. So this explains how this matrix equation 11 is formed. Then we go for step 2. It is just, you know, alternate direction. So now we will have I sweep. We'll progress from I equal to 2 to I max minus 1, and j will vary, and in equation 2 will vary j from 2 to j max minus 1. So this will form the tridiagonal matrix, and values at n plus 1 level are not known. These are the unknown values n plus 1 level. And again you can see the first equation that is in this direction, I2 t I1 by delta y. So basically this when we are here, we have to apply basically symmetric condition here. So this is a symmetric condition here, ti2 minus ti1 by delta y, and when we are here again we will get basically the top boundary, which is again convective boundary. So that is Tij max minus Tij max minus 1 by delta y, that means del t del k del t del y plus h t equal to h into t infinity. And here it is t, at the bottom it is ti1 minus ti2 or ti2 minus ti1, whatever way you write, set up del t del y equal to 0. And again all intermediate points again will be guided by equation 2. If you recall, just the equation 2 will be the all intermediate point. So these are j equal to 2 to j max minus 1, and ry minus ry by 2 into ti j minus 1 1 plus ry into tij plus into tij minus ry by 2 into tij plus 1. Those are unknown terms, and right hand side is known, and that is how this tridiagonal matrix is set up. Again, like we checked in the last case, see first equation you can get here tj1 ti1 and ti2 in this column. Now basically j we are varying, and I is kept fixed. For each I will vary j. So this is I sweep. I will first will fix I equal to 2, will find all the values, then go to I equal to 3, find all the values, I equal to 4, all the values, and when we are fixing I, we are basically forming a tridiagonal matrix for that I. So here we have done that, and here you can see again the last equation, like k del t del y into ht equal to ht into t infinity. Here also last equation is basically interpretation of this. You can see minus k del t del y with j max minus 1 term, then k by delta y plus h with ti j max term, and right hand side is h t infinity, equation 12. So basically we are supposed to get a tridiagonal matrix where this x vector is unknown and the c vector is known, and this tridiagonal matrix D is the diagonal, B is the immediate subdiagonal, and A is the superdiagonal. So we will set it up. We will initialize delta x, delta y, h, k, delta t, t old. Now we are setting up the algorithm. So basically these are the arrays or variables we are discussing, and we are initializing. We are defining delta x, delta y, h, k, delta t, t old. This is a subscripted array we declare, and t new, another subscripted array we declare, and dimension of this array are the maximum points in arrays or maximum points in I and j direction. Apply initial condition t old I max j max equal to t naught. That means the initial temperature, which is higher than the ambient temperature. Now two sweeps for each j except for j equal to 1 and j max. We for each j we form the tridiagonal matrix. So sweep initially in the y direction for each j, that is except for j equal to 1 and j equal to j max we have said. So that is why you are calling it j. We are going from j equal to 2 to j max minus 1. But for each j we are forming tridiagonal matrix, and this is if we define a tri a b c d rx, and these are the values array variables, namely a b c d rx are obtained from equation 1, and you can see c1 is 0, like if you equation 1 or equation 11, c1 is 0. These are all intermediate c2, c3, c4 value, and this is my finally cn value. So C max is T infinity, and all these intermediate Ci values are this. Similarly, these diagonal values, if we calculate, so we can get from here also, these are all diagonals, right? So you can see that first value is d1 is minus 1, all intermediate di's are 1 plus rx, and finally d max is k by delta x plus h. Now these a values, we are calling it a, as you can see, a1 is 0, ai's are minus rx by 2, and ai max is minus k by x. Although we are patterning it after this tridiagonal matrix, we have called our d arrays are diagonal arrays, our c arrays are same, but our in this problem these subdiagonals are defined as, in our current problem, a's. Just a little change, I think you will be able to understand. a1 equal to 0, ai's are all minus rx by 2, and a max is minus k by x, and b's are just we are calling super diagonal sub B. So you can see B1 is 1, all Bi's are minus Rx by 2, and B max is 0. So Bi max is 0, and that is how we get the all the arrays of the diagonal, subdiagonal, superdiagonal, these arrays, immediate subdiagonal, immediate superdiagonal, these arrays, and see the column vectors. And once we get that, we basically we have got the entire tridiagonal matrix, and from the tridiagonal matrix, finally the vector that we evaluate is x1 to xn. So that is what we will see. So the tridiagonal system returns xi array. So this is how each tridiagonal matrix will give us xi array, means all these x points, temperature points. So store T nu ij equal to xij. So that will give the temperature distribution at each point. Then again we will go to next j, we will get next all points. So we will keep on varying j. So but this new array we will store, and for each array after storing, what we will do, we will apply boundary condition which we have not applied so far, because if you look at the boundary condition for equation 1, see we have applied 4 and 6, but we have not applied 3 and 5. So 3 and 5 can be applied now, because we have found out these, we have found out next j point, all the up to we have got j max minus 1, all these points we have found out, but we have not found out these points and these points. But these points is from 3 and this is from equation 5. So this is basically here again at each point. Now we have to vary I and set del t del y 0 at each point. Similarly, we have to vary I and del t del k del t del y minus k del t del y equal to h into t minus t infinity. We have to set an at all these points. Then we complete the task for the j sweep, and sweep for each I except for, then we again change the direction. So for each I, then we go for each I, then we go for formulation of tridiagonal matrix in j direction, like this one. For each I sweep we will do now tridiagonal matrix in j direction. So that is what is the next level. But this is just what we did in 3a, sweep for each j. We will form tridiagonal matrix from involving I equal to 1 to I equal to I max minus 1 point. Here also we'll repeat the same thing in alternate direction. That means we will fix I points except for I equal to 1 and I max, but any intermediate point, say I equal to 3. Then we will vary j equal to 2 to j max minus 1, and we will form from equation 12 a tridiagonal matrix. We'll solve that. All the points will be evaluated. We'll go to j equal to 3. I equal to 3. Sorry, I equal to 3. And again, we'll vary j equal to 2 to j max minus 1. We'll form the tridiagonal matrix. We'll solve it. We'll move to I equal to 4. Again, j equal to 2 to j max minus 1. Again, a tridiagonal matrix. Again, we'll get the values of at all the points. Here we have written that second tridiagonal sweep has to be done for all i's except I equal to 1 and I max. Call the subroutine try a, b, c, d, r, y, where the array variables a, b, c, d, r, y takes the values from equation 12, which again returns xi, the unknown matrix, and update t nu ij equal to xi. And then again apply boundary condition equation from equation 8 and 10. Like here, after having evaluated everything, we had to apply 3 and 5 in order to set these two boundaries right, these two boundary correct. So similarly, when I equal to 1 to I equal to I max minus 1, we will sweep and we will form tridiagonal matrix for each I point involving all j's. After completing this, we will see this row will have to be done, and this row, this column has to be done. Sorry, this column has to be done, and again this column, and this points, column of points have to be calculated from equation 8 and 10. Like here, these rows of points we calculated from 3 and 5. So similarly, 8 and 10 will have to calculate all these confining boundary conditions, or set up confining boundary correctly. And then one complete time step is over. We'll go to next time step. That is how the calculation will progress. If it is required to predict the temperature field at a specified time level, then divide the total time duration by 4 or 5 equal divisions, and each division is counted as the time step, delta t. Use step 3, that means these two sweeps, j sweep and I sweep. So use step 3 to complete the calculation for each time step. Having calculated the temperature field, after each time step, initialize the temperature field by the most recent value. That means, for example, you have to go find out a hot plate temperature after 10 seconds. So maybe you divide 10 seconds by 4 parts, 2.5 second, 2.5 second. And after each 2.5 second, you find out the total distribution, and now this will be the initial distribution. From here again you go to delta t. This will be n, from n to again go to n plus 1. When you have gotten n plus 1, then again that will be n, you go to next n plus 1. So that is how, if when you reach the desired time level, you go to 6, that means stop. Some problems are such that, such cooling problem, you just define it little differently. Instead of knowing temperature after some given time, you want to reach a steady state temperature. In that case, if you are required to reach the steady state temperature, then take a time step that is reasonable, because here you have no restriction by stability. You can take larger time steps, but this cannot be also too large a time step. I'll discuss this point later. Even though there is no restriction, we cannot arbitrarily take a very large time step. So reasonable, and calculate the temperature field iteratively using step 3. At the end of each time step, compare the temperature values at each location between two time steps. Each location, that means T2 2, T2 3, T4 4, T4 5, same location, what was the temperature at N and what is at N plus 1th level. And this discrepancy you survey over the scan over the entire field. Now check if the maximum discrepancy at any ij location, you have to keep on calculating till this and this maximum discrepancy can occur at any point. So wherever it occurs, this you will keep on iterating and applying boundary condition till it falls below a specified value, say epsilon. Epsilon may be 10 to the power minus 3, 10 to the power minus 4, something like that. So basically we are reaching a stage where temperature is not changing. Changing after third decimal place or fourth decimal place is not a change in temperature. So basically, specified, as I said, that check the maximum discrepancy at any ij location falls below a specified small value, say epsilon. Effectively, maximum discrepancy at any point, ij point, it can occur anywhere. After each time step it has to be can, till the maximum discrepancy falls below epsilon. And if it does that, that means you have reached steady state, you go to step 6. Else go to step 3 and repeat. So I have just taken up this example because this is the way you have to set up a problem. This is the way you have to plan an algorithm. And then you go for programming. For me, programming can be done in any language, whether you use C or C++ or Python or Fortran 77, Fortran 95. Fortran 77 and Fortran 95 are scientific programming language. These are languages. These are used by several numerical algorithm subroutines. But there is no restriction. If you know, you can do that. Otherwise, you use C, C++. Some of you are, these days conversant with Python. You can even MATLAB programming. But main focus is you set up your algorithm correctly. If you can set up your algorithm correctly, whatever language you use doesn't matter. You will get the correct result. So we have done this, all this arising out of this discussion. It excites me to give you a problem. Also, probably it will be very, satisfying experience for you if you can solve this problem by yourself. So you really now know everything. You have to, again, just what we did, repeat that problem with numerical data. Consider a chrome steel block. Z direction is infinitely long. Again, I should have written something else. Not infinitely long. It is very long. It is so long that it's not comparable with x and y direction dimensions. So whatever will happen at any x and y, it will keep on repeating if z direction is very long. So only end effect will be something, but it will not influence the entire rod. There may be some little end effect. So it's a read infinitely long block with a very long block, not infinitely long block, with side walls 8 centimeter. So x and y dimensions are 8 centimeter. Alpha is 1.6 into 10 to the power minus 5 meter square per second. Thermal conductivity is 61 watt per meter second. And so thermal diffusivity and thermal conductivity, you can see. The block is initially at a uniform temperature T0. As I said, it's a heated block. Temperature is 325 degrees centigrade. it is suddenly exposed to cool stream at 25 degrees centigrade. The heat transfer coefficient between the air and the surface, that is H, is 400 watt per meter square Kelvin. By using a 10 by 10 grid mesh, find the temperature distribution after 20 seconds. So now you know delta X, you know delta Y, you know H, you know initial temperature, you know the time interval after which you have to determine the temperature. All property values are known after 20 seconds. Maybe you can make smaller time steps. Maybe after each if you set up a program, it doesn't matter. Maybe after each 2 seconds, 2 seconds can be your intermediate, your delta t. So, or maybe 4 seconds can be your delta t. So then it will be a 5, iterations in time direction. So after you choose any value. You can take 2, you can take 4 seconds, you can take 2 seconds, and but for each 2 seconds or for each 4 seconds, you have to progress, through a time step of delta t by 2 from n to n plus 1, then n to n plus half, then n plus half to n plus 1. Then that will be the initial value. From there again n plus half and n plus 1. So this way, after 20 seconds, what is the temperature distribution on the block? That means temperature at all 100 points, 10 into 10 grid mesh, you have to find out and submit. I will formally give this problem as an assignment so that all of you can get credit for this, but practice it. Practicing it will be really useful. It will be a very, very firm step for confidence building. Once you can solve, you get really a result from your computer for all 100 points temperature, and they are reasonably correct to second decimal place. That is good enough. You will have the confidence that you can formulate a problem and you can solve the problem, which was seemingly unknown to you even a few days back. Thank you very much. I'll stop here today. Thank you.